Hello, everyone. This is a presentation that I gave at the Society for Industrial and Applied Mathematics meeting on parallel processing for scientific computing, long conference known as SciMPP. And specifically within that conference, I presented in a series of talks on the progress and lessons learned through the ExaScale Computing Project, which just ended this past December. What I'm going to specifically cover is focusing on one of the sub-projects, the machine learning on project as part of the ExaScale Computing Project known as ExaLearn, and drilling down even further the work that my team had done on being able to add artificial intelligence into machine learning or into conventional simulation workflows that we use a lot on high performance computing. That's the overall or title of the talk and where it was placed, but this was a particularly interesting talk for me because I had never been to a SciM meeting before. So it was not only fascinating to be able to hear talks on subjects that I wasn't very familiar with, but also to understand a little more how my colleagues in applied mathematics think about and structure problems such that I can better communicate with them and find those opportunities where I can really use their expertise in a way that benefits everyone. So with that said, we'll talk through this presentation, which again, to recap, is covering work that myself and others did as part of the ExaScale Computing Project's effort on machine learning. And when I say myself and others, that's actually a fair number of people, not just specifically within the ExaLearn design team, and that spans three colleagues, Sutane, Jenna, and Henry, who are out of Pacific Northwest National Laboratory, but also Ganesh Sivaraman, who was another scientist at Argonne during the extent of this project. Beyond that specific core team, we had many collaborators from the chemistry side through the Joint Center for Electrochemical Storage Research, namely Rajiv, Larry, Naveen, Hugh, and Paul, who I worked closely with on this work to ensure that it really lined up with scientific objectives, as well as many others at the University of Chicago who were either part of the ExaLearn team in general or others that I worked together with to really build something that we found to be very effective for using AI and HPC. HPC being our high performance computing. With that said, let's go into the real meat of the talk. The overall context of this work is that while there are a common class of applications that are deployed on supercomputers, which run many different kinds of tasks, all independently of each other, all at the same time, which they scale very well. You can use a lot of computing power on the high performance computing system. They are not known to be the best kinds of applications for showing off the HPC. Because I mentioned that all of these individual calculations, whether they're, say, different materials being studied in a high throughput design campaign, or different parameters used in a parameter sweep to kind of learn how different variables affect certain observed behavior, like in cosmology simulations. Those independent tasks don't necessarily coordinate with each other. So there's a large component of what makes a supercomputer really great, the ability to have a lot of communication between different computers that isn't shown off. So what we wanted to study is how we can take these applications and rethink them in a way that makes these independent tasks more coordinated to each other and therefore make better use of any supercomputing system, and particularly those new classes of ones, the exascale systems, that have shown up just in the past few years. So with this overall context of we want to take these campaigns and be able to make those tasks more interactive with each other, we thought at first, how is this typically done? Now, the way a high throughput campaign is typically performed is a human starts with an understanding of what they're trying to solve. They use that to enumerate a list of tasks that are then executed in rapid order on a high performance computing system. After those are finished, or perhaps after a good chunk of them have completed, a human will go and refill the queue such that the supercomputer is kept continually busy. Now, this is an effective technique People have been doing these kinds of human-in-the-loop searches for decades. They're not going to continue to scale because the ability for supercomputers to do more work faster is increasing, and humans are not getting better at processing data faster. So really what we need is to add some more automation into the process. That is, to take this task of deciding what to do next, which is typically done by human intelligence, and replace that with an artificial intelligence, such that we can make all of these tasks operate together on HPC, and we've now got this nice close coupling loop that will ensure that our use of the high-performance computing system really leverages its ability to have many tasks that all depend on each other. And we're hopeful that this will not just lead to better utilization on the HPC, but because data can be processed sooner and faster and decisions can be made more rapidly, we can also have better scientific outcomes. So with all of that said, the real core challenge of being able to achieve that vision is there are many ways to tie that decision-making system into a workflow of tasks. You could imagine doing them in batches, where, say, you run a set of 4 tasks, wait for all 4 of them to complete before deciding your next batch. And this is great. I'm making my decisions with the maximal amount of information. I'm waiting to see the effect of a decision before I move on to the next one. But you can see here that if there is a variability within the tasks I perform in that batch, I get this classic underutilization pattern. Now on the other end, I could create a long enough task queue that as I kind of wait for tasks to complete before running my next decision process, I always have work in the queue. And these are 2 ends of a spectrum. There's obviously at least some things in the middle. I have a shorter queue, yet I wait until data is available before making a new decision that hopefully illustrate to you that, well, there are at least 3 policies in how I could imagine putting this AI task into the computational workflow. But what if we imagined that there are many other ways that better leverage the characteristics of the task or the decision-making process? Or what if I had different types of decision-making that are all interleaving together? And this is the kinds of questions that motivated us kind of very early on in this project during the past 5 years. And that's what I'm going to be talking to you about today, of how we ended up addressing them. In order, that's going to be explaining the toolkit that we built to experiment with these different approaches for steering computational campaigns. Explain how we took that application and we're able to address some of the problems in getting it up from something that runs nicely on a laptop, like I'm showing you where these pictures were acquired, to something that could eventually move us to ExaScale Computing. And I'll give you an indication about what we're going to do now that these ExaScale computers are available. With that said, let's first talk the basics of Colmena. Colmena is a tool that we developed to be able to explore these steering policies. And it was built around the idea that there are many different kinds of rules that one may want to implement when designing the optimal steering strategy. You could imagine that I have something very simple triggered on an event. Submit a simulation as soon as another completes. That's easy. So I've got some event-triggered logic. I've also maybe want to express rules that are retrain a model after 8 other calculations have completed successfully. So there's some notion that I'm going to have to define these rules with some conditional logic in them. I could have rules that also adjust the resources on how tasks are deployed on the supercomputer. And all of these together really spoke to the team that we needed some ability for people to express these event-driven logics separately from each other in a rich programming environment. And additionally, that we want to be able to do this in a way that is decoupled from the actual problems of enacting those decisions on a high-performance computing. Actually, running workflows on a high-performance computing system is a massive challenge. We're not talking about those issues in the talk today, except for kind of where the little slices of pie we had to address in order to make our application scale. But suffice it to say, we knew that there was a massive amount of people already working on the how do I run these decisions on HPC. So we wanted to do it in a way that we could reuse their work and their creativity. So what we came up with is a simple programming model. Colmena applications are decomposed into three different parts. A thinker that includes everything that's really specific to how I execute a high-performance computing campaign. It has a series of computational agents that run as different threads that interface with a task server that actually does the work on delegating to the HPC system. That task server is what interfaces to a workflow engine. We partnered with the ExaWorks project in order to tie in Colmena to workflow engines like Parcel. Parcel being one that also funded some of the other people working on our project, so it was a very easy place to start off with first. So we've currently got one ability to use Parcel and FuncX. We could write a Dask one, but right now we focused on the front half of this puzzle. How do we make that thinker as good as possible? So what we came up with is a Python-based programming model. We like Python since a lot of scientific computing tools are in that. And the work that we have here isn't necessarily performance critical, not in the way that the numerical codes that your application is running. So in order to write that thinker, it's just a process of being able to create a subclass that defines what information is shared between the agents. Then each of the agents has Python functions that are marked with a decorator, like the result processor decorator, which means that this function will run as soon as a task with a certain topic designation completes. And you can see here this consumer process takes the result, checks if it's the best observed so far. If so, update some information, and if we've completed enough tasks, trigger the simulation to stop. So hopefully here you can see that these Python functions define very simple logic to defining a computational campaign, and you can create many of them together to create this sort of interacting environment. It's also built in Python. We use as much standard Python as we can. All of the communication between threads like this done are Python threading objects. Done is an event. And hopefully all of that makes it relatively simple to integrate this in with other Python code. The other part of the Colmena application is the task server. Here you define your tasks or your methods as Python functions. You pass them to a workflow engine. Here we've got one built on Parcel that takes those functions, a definition of what resources it's allowed to use for each of them. And then finally, this just becomes a sub-process you run that will talk to your thinker over some queues. And what you end up when you combine these two together is an application that looks like this. This is an active learning algorithm. We use it to design molecules. And the way that it works is it runs these 6 agents that each have a simple task. The quantum chemistry score, all it does is wait for resources to become available. As soon as one is, it starts a new NWChem simulation. That gets stored in a database, used to update a machine learning model, that gets fed into inference, that eventually is used by this machine learning recorder application to update the molecule queue, which is used to determine which tasks to run next. So here we get this on-the-fly learning behavior designated as a set of separate agents that we can combine together to form some emergent type behavior. Here's an example of what this looks like running on high-performance computing. If you've seen any of my other talks, this is one run that we performed in 2018 on the Theta supercomputer at Argonne, now decommissioned. And what you're seeing here is over time, which node or how many nodes were dedicated to each type of task by the color, and whether they were actually doing work or not, based on the shade of that color. Dark meaning they're actually doing work. And you can see that the way that this simulation campaign progresses is we start off by running inference to determine which tasks, and I use all available nodes so I can get that answer as soon as possible. Once that's done, I have no new data on which to train a machine learning model, so I'm not going to spend any resources on how to decide what to run next, and I dedicate all 1,000 nodes to simulation. Eventually those complete, After enough complete, I start training. After training completes, I start inference. Again, dedicating as much to inference as possible to make it short so I can get that updated decision quickly. And this iterates back and forth over the course of hours. And what we ended up finding is that by implementing this complex policy where I update the machine learning models and update my decisions every time 8 complete, I end up with about 10% more molecules with a high property found at the end of 6 hours than if I never updated that machine learning model or if I ever used machine learning at all. Uh, there I'm getting probably on the order of 100x speed up. I didn't end up finding any molecules after 5 hours, and I never did run a additional test to see how well it did after 6. But clearly you can see that there's, of course, a massive improvement using machine learning to identify those good molecules, but that you can eke out a little more by running these complex policies. And that's really all we were trying to do with Colmena, to make it possible to put that AI and use it as most effectively as possible in a time span faster than when a human could sit down and process the data. Here I'm making decisions about what to do next every 45 minutes to an hour. Now, you may have noticed on that slide that I showed you that there were a lot of points where I was asking the machine learning, or the supercomputer that is, to run a series of computations, and they weren't actually happening. There are all these regions that are light shaded because the machine learning nodes, the actual workers aren't running the tasks that they were supposed to. And there are a lot of different reasons for that. The first of which, and this is one I don't have a solution for, is that loading in machine learning libraries takes a long time, especially on a distributed file system like those attached to supercomputers. So it can take like 10 minutes for a node to load TensorFlow and then start executing tasks. So that's why I have these regions of underutilization. I'm asking the nodes to run TensorFlow. It's taking a long time to run that, to bring that into memory, so nothing's happening. There's some cool ideas about how we can speed that up. This is a paper from Alok, one of the PhD students in the group that I work a lot with, who's got some cool ideas on how we could change applications and how they run on HPC and Python. Now, so that's going to be a little bit of a downer, but we were succeeding on speeding up some of the other calculations. Let's take a look at this inference task that started at the beginning. Here, I'm asking to run 1,000 nodes, and at any point when you start running large numbers of calculations, it's always good to check, are we actually using all of those available resources? And what we found early on in the project is that we were not. This here is showing the evaluation rate, how many molecules we study per second, as a function of the number of nodes I used to do that. And our first implementation worked great. It had this linear scaling, more nodes equals faster, up until you hit around 500 nodes. Then it started to undergo a process where the more work we added to it, it actually slowed us down slightly. And that was because we were running into a problem where our results stayed on the compute node for, in some cases, 1 or 2 minutes, where in very small node sizes, it would typically be under a second. And this to us suggested that the mechanism that we were using to bring the result off the node and pass it back to the thinker was getting clogged. So what we wanted to, or we eventually decided to do, was create this secondary channel, which we called a value store at the time. It now goes under the name ProxyStore because that's a tool or the software library we use to implement this, where data is directly passed from the thinker to the worker nodes and back over a high performance data transfer fabric such as Redis or some of the more kind of recent advancements in distributed and streaming data infrastructure. And what this means is that the data is only undergoing one hop, directly from compute node to thinker, and bypassing all of the intermediate steps, creating copies and transfers over protocols that are not designed for large data transfer, leading to very slow behavior. So by implementing this value store, we were able to scale well beyond 500 nodes. In fact, getting up to around 2,000 before we started seeing performance degradation. And going back to that kind of problematic behavior I showed you earlier, where results sat on the compute node for a minute or two. Here, we only found about 8 seconds during this particular task. We completely squashed that transfer time, keeping it to about 100 milliseconds regardless of the size of number of nodes we used. So overall here, a big success. We were able to increase the throughput of our application by adding in this secondary channel. And we tried to do it in a way that limited the amount of actual coding work we had to do. That's where this tool called ProxyStore comes in. ProxyStore works by taking a Python object and replacing it with a reference that after you try to use that reference, it acts just like the original Python object. So this means that none of my Python code has to change. If I use a proxy and I pass that around the application, I can avoid having to refactor my code. And with this proxy, I did say it was a reference. It is referencing a copy of the data stored in a high-performance data transfer tool like Redis. And we do this in a way that these proxies can either be created automatically, which is great. You can use ProxyStore in your application with adding 2 lines of code, or you can do it manually, which allows you to have a little bit more control over whether, say, the same data is used on multiple tasks or things like that. Other thing that I'm happy to report, ProxyStore is not part of Colmena. It's not integrated with our workflow engine. So if this is something you want to use, you don't have to buy into our ecosystem. And I can say I've used it very extensively, and I'm really happy with the implementation and documentation. Greg and Valerie, the 2 folks who have been working on this, have been doing an excellent job. All right, so the other problem we encountered was the amount of time it took to update our decisions was slow. It would take about 45 minutes to update our machine learning model, or sorry, about 30, and then another 30 minutes to 45 to use those updated models to change our decisions. And this was a process due to the fact that the computer we were using was really good for these simulation tasks. It has a lot of CPUs per node, and WChem runs very well on that. That many-core architecture did not work well for our machine learning models. So what we eventually wanted to do was create a ability to offload those AI computations to a type of computer that worked very well for them, such as the rich set of AI accelerators that are available through Argonne's AI testbed. So happy to plug Argonne and all of the interesting vendors who have supplied us with test systems that we can use to explore. And once we introduce the second type of computers, we start going down a problem where those data transfer issues I talked about earlier are amplified. My different types of hardware usually don't share a file system, so there's security implementation or implications. I want to bypass talking about security today to focus on the other problem, that moving the data between systems means I'm going to have to make several copies. So here we use the ProxyStore library again to be able to transfer that data between systems using a well-suited transfer technique using Globus's grid FTP to quickly move data between systems. And we also were able to use the kind of ability to write complex steering mechanisms within Colmena's Thinker to be able to hide the latency such that there were only 3 places that it mattered. The latency that is in sending data to the remote system. Those include sending the machine learning models and data sets for retraining. That we found with our implementation takes about 4 seconds. Using the machine learning model to run inference, sending the copy of the model back to the thinker, for quality control before we send it out for inference. Takes another 4 seconds. And additionally, we had a fair amount of latency in simulation, about 10%, or sorry, 100 milliseconds, which is less than 1% of our overall simulation time. And the interesting part, so these performance numbers are good. They compare well against reference implementations using other techniques for transferring data. The real part that speaks to me is that our science outcome is unaffected. Here, I'm showing you the number of molecules we found as a function of compute time expended using those 3 different reference implementations. The one that uses a cloud service to transfer the data performs basically the same as our other 2 reference implementations. And the cool part about this, and you can read more about it in our HCW paper from last year, that we were able to do all of this without needing to open SSH tunnels between the different hardware, which has security problems. You may bump into policy issues, and it's just a nuisance to keep all of them alive during the course of a multi-hour application. So in short, same science output, less effort. Other problem that we ran into, and this is one that we're still tinkering with, is that there was a large amount of underutilization at the end of the run. Here, you're not showing the fact that the nodes weren't doing anything, but that the work that they were running did not complete before the end of the allocation, and therefore was left kind of unutilized. Hence, I mark the node as unutilized. And this is a problem that we partly addressed in later work by adding a checkpointing mechanism, such that the next time we ran the application, it could restart from the same quantum chemistry calculations. But the one thing that we wanted to explore also is how could we reduce the length of these tasks overall, such that at worst, you have a smaller period at the end of the run, where the data you're computing on these simulation tasks doesn't go to waste. And here, we decided to go about that by breaking our pipeline of simulations from one big monolithic task into many small ones. So the science detail, we were computing something called the adiabatic ionization energy, which has multiple steps to it. I have to take a molecule without any charge, minimize it. I have to compute its energy after I induce a charge, and then I have to find how to change the structure such that it lowers energy. This gives me multiple steps of the calculation where I can reevaluate whether to continue on the next one after each. I can train machine learning algorithms that say predict, given the information I have about this neutral geometry, how well it should perform after the next 2 steps. I could do the one after this increase in charge. I could guess further. And this allows me to introduce a policy where perhaps I only run the calculations that are most promising after each step. And I don't run every molecule at the highest fidelity. Say I run for every 4 molecules that I run for the first step, I run 2 at the second, and I run 1 at the third. And in that way, I can really budget my computational time to only focus on those best molecules. And additionally, I undergo smaller steps so I can ensure that data is sent back and processed sooner, and I get that underutilization. That ends up having to write a more complicated policy, which brings me back to the whole goal of Colmena. Our ability to write these complex steering strategies as simple Python functions independently of each other made it easy to explore with how to run and build one of these large applications that have these intricate steering policies that perhaps leverage different unique characteristics of your application. And to give you a little bit more idea of kind of the types of things you can build with Colmena, let's talk a little bit about our target applications. The first target applications, that is, for Aurora, the supercomputer now up and running at Argonne, and that we've been experimenting on for a couple different science projects. One of which is the molecule design work that we've been studying since the beginning of my time on the project back in 2019. Nowadays, we've introduced those multi-step, multi-fidelity machine learning efforts, and we've also taken the application from its really early prototype stages where I was really the only one running it to something where I've had time to document all the parts, rework them based on all the knowledge that I've picked up before on how to execute these campaigns well, and put it behind an interface that allows you to have the ability to change what sort of science you're doing without having to touch as many internals of how it's actually done. So you can take a application and define how to do active learning and maybe these 15, 20 lines of Python code, or you can implement something like we've done with multi-objective learning with multiple levels of fidelity using 2 different computational codes and advanced neural networks, all using the same application framework. So that's something that we've been putting together. Feel free to go on the GitHub if this is something that interests you, but it's one of the things we'll hopefully be writing about more as we port it to Aurora. Another thing we're doing is mixing different kinds of AI. Here, this is work that I've been happy to be a part of, along with a team from University of Illinois at Urbana-Champaign, the University of Illinois in Chicago, UChicago, and Argonne. I always like projects that are able to mix a lot of different institutions and backgrounds together. In this one, we have a couple different types of simulation and machine learning going on. I have a diffusion model that invents moths that I then assemble using conventional simulation tools before passing them to another set of AI tasks to determine which of these moths are most likely to succeed when I eventually reevaluate their property or evaluate their properties using simulation code. With Colmena, we're able to implement these different kinds of tasks, be it AI or simulation, define how they work together, and execute them on a high-performance computing system, all at the same time, all collaborating together. Another one that we've been working on uses a very similar theme. It has a large language model that invents protein sequences, and we implement a multi-stage screening pipeline where I go from the ability to generate hundreds of thousands of protein sequences, fold them, evaluate different properties of gradually increasing fidelities, and doing this, of course, on hundreds or thousands of GPUs with each different type of task running at the same time. And with this, we've been able to find engineered proteins that perform better at certain catalytic tasks than others, and it's something that you can read about more in a paper that was published in last year's SC workshops. So with that said, that covers at least the 3 main applications that we're working on with Colmena. I'll probably be posting YouTube videos as we build more. And this really brings me to the end of my talk, where I wanted to go back to that original goal we had of taking the abilities for AI to replace human intelligence and using them most effectively. We came up with this ability to express sophisticated policies where you can take the different types of calculations that are needed for AI, mix them in at the appropriate points with the different kinds of simulation tasks, and build these hybrid applications that mix different kinds of calculations together in a way that would be difficult to express in conventional workflows, yet can lead to some improved scientific performance depending on the application. So at this point, I'll leave you with just a few summary points. The key work that we did as part of the ExaScale Computing Project was build this tool Colmena and then integrate it into a couple different applications. You can find all this information about the code on our Read the Docs, which will point you to the papers that I've referenced today, as well as a few other YouTube videos, which will sound familiar. This is the wrap-up talk of a long series of papers. And the code is still going to be worked on. It'll still be a part of the ExaLearn the ExaLearn GitHub organization, though I may end up moving it depending on how we need to restructure and now that the ExaScale Computing Project has ended. One other thing that I put in this talk as backup, no one ended up asking me about it, but I thought since I'm recording the YouTube video now to go into, is where you might not want to use Colmena. There are a rich set of computational tools out there for integrating AI into simulation. And Colmena doesn't solve all of those use cases, particularly if you've got a very large task throughput. Colmena will not support it very well. The best performance I've seen is making thousands of decisions per second. And while we could play some games to accelerate that further by perhaps running multiple Python processes to execute decisions, this might not be the best tool for you. You might want to consider something like SwiftT workflow library, which has a much higher performance threshold than the ones that we use. Additionally, if there's a long latency between tasks of human that perhaps involves a human in the loop, consider things like AWS step functions or Globus Automate to be able to tie the different parts of your workflow together. And additionally, there are a few other things like inter-worker communication, which doesn't work with our programming model. Those tasks are designed to be independent of each other. Only the thinker has knowledge of how many other tasks are running and how to tie them together. Yet there are tools like decaf or Ray or SmartSim that will allow you to write that kind of intra-worker, or as I believe decaf terms them, in situ workflows. Additionally, Colmena is just the ability to integrate these Python policies into workflows. It doesn't come with anything like hyperparameter optimization, but there are tools like DeepHyper or RayTune that do that kind of work, that can allow you to fill in this gap between a lot of parsimony and how you define your workflow. Other tools like, as I mentioned, DeepHyper that focus on hyper-performance optimization and do it well. LibEnsemble, which integrates into math libraries that can allow you to write your application faster. Or there are tools like SmartSim or Ray or decaf that can allow you to write a more purely decentralized workflow than you could with Colmena, at the expense of having to deal with more types of communication that you need to implement. So in short, Colmena is just one of a many different set of tools within a library that you should be considering, but as we illustrated earlier, it works for a broad variety of problems when you can figure out how to separate each type of task into a different simple policy. That's all I've got to say on this talk today. Feel free to leave comments on the video if you have any other thoughts, or feel free to check out these websites and their associated papers. So thanks again for listening, and I hope you're enjoying your afternoon.